Okay, question 3. It's a buckling problem, and what we got to do, you've got a square section, column, 200 gigapascals, Young's modulus, subject to eccentric compressive loading, shown in figure 3, because that's been displaced by 10 millimeters off the edge. The second moment of area, calculate second moment of area, calculate the critical, or they've been funny. Second moment of area, calculate the critical load for buckling, calculate the radius of gyration, and calculate the aspect ratio. Now that doesn't make any sense because aspect ratio should be probably depth divided by width. I think this means slenderness ratio. Calculate the maximum deflection. Okay, formula sheet, everything's formula sheet. Okay, first part A, you should be able to do without looking at your formula sheet by now. But if you don't, let's find it for you. So it's going to be one of these guys. What I will do, obviously the top ones are for rectangle type cross sections, and then we got for a circular one. So I'm going to take an x-axis through the neutral axis there, xx through that direction. So we're going to use this one here. The depth will be this distance d, the breadth will be this distance b. So I is going to be given as b, d to the power 3 over 12. The breadth is 30 millimeters. The depth is 30 millimeters to the power 3 divided by 12. So that's 30 to the power 4 divided by 12. Let's use a calculator. .67500 millimeters to the power 4. So let's work that out in terms of SI units, make it in terms of meters. So divided by, what would it be, a billion? That is 67.5 times 10 to the minus 9 meters to the power 4. So that's part A done. Part B, we need to look up the formula for critical load. And there it is, next to the other ones we want. So the only problem with this formula is what the hell do we do for K? And I can never remember them, but the only thing I can remember is that K is either going to be 1 or 2 for most problems. So in our particular case, we've got a fixed end and a free end, in which case K is going to be 2. If you've got a truss type problem with kind of like pins either end, then K would be 1. If you want to look at all the cases, you need to go to Johnson, Beer and Johnson. I can find that. Yeah, here we go. And they've got a diagram there. Showing the various examples that you could have. So you kind of got to memorize that diagram, but as I said, it's either going to be this case here, K equals 2, which is what we've got at the moment, or it's going to be this case, maybe in a kind of truss system, K equals 1. Okay, so we should be able to plug in our numbers. Let's pretend we've written this out. So our critical load is going to be pi squared 200 times 10 to the 9 67.5 times 10 to the minus 9 divided by K, which is 2, and convert my 750 millimeters into meters, 0.75, square it. So that is going to be pi squared times by 200 to the 9 times 67.5 times 10 to the minus 9 divided by 2 times 0.75, close the bracket and square that. What's the load value? So that's 59.218 and load, so therefore it's newtons, kilonewtons. Now let's compare that to the load being applied. So the load being applied is 40. The critical load when it will buckle, if you apply that load in the middle, is 59. So I suppose we could make a statement along the lines of, if load was at neutral axis or the centroid, it would not buckle. Okay, and that 59.2 is a nice number compared to 40. So it's safe. We got another 19 kilonewtons there we could apply in the middle, and we wouldn't expect any buckling to occur. Right, what next? Then part D. Part C, the radius of gyration. And looking at your formula sheet, I cannot see a formula for radius of gyration. I don't think there's one there, but it's easy enough to remember. So second moment of area equals the area times radius of gyration squared. Therefore, radius of gyration equals second moment of area divided by area square rooted. Let's work in millimeters. So we're going to have 67500 divided by area, cross-section area will be 30 times 30. So what's that? 67500 divided by 30 times 30. Let's take the square root of that. That gives me 5√3. Give you an engineering answer, 8.6603 millimeters. So I was working in millimeters. Now, assuming this is slenderness ratio, again, we don't have a formula for slenderness ratio. I can see on the formula sheet, something you'd need to memorize. So slenderness ratio is the effective length divided by the radius of gyration. So that's going to be K times L divided by RG. So 2 times 0.75. Actually, it's in millimeters. Let's stay in millimeters then. 750 divided by 8.6603. So working in millimeters now. 2 times 750 divided by 8.6603. Okay, wow, we got a big slenderness ratio there. Anything above 20 and you are in trouble. So I am expecting this thing to be buckling. Right, so part D, the maximum deflection. So we want to be using use this rather weird symbol for deflection. You find this in quite a lot of textbooks. They use the new symbol. Okay, so notice that we got a choice. We can either use this bit here or this bit here. Now we've just calculated the critical load and we know the load, so this bit here makes more sense to use. So deflection equals E. What's sec? That's 1 over cos. Pi over 2, so you've got a choice. You can either be in radians or you can be in degrees. So let's use it. Can I switch to radians? I'm going to switch to radians and use pi over 2. Right, my critical load, I can remember that was 40. Oh, sorry, my applied load is 40. My critical load is 59.218. 59.218. Notice again, I've been a bit naughty there. That's in kilonewtons, that's in kilonewtons. So I'm okay about that. So I need to put that all in a bracket and then take away 1. What I do is I work out this thing here, take it step by step. What's E? Well, E is the distance from the neutral axis to where the applied load is. So the neutral axis is going to be 15 millimeters away from that edge there, and the applied load is 10 millimeters in. So this distance from here to here is going to be 30, take away 15, take away 10, so it's going to be 5. Probably an easy way to work it out, but that's what my E will be. So 5, we could work in millimeters here, so 5 millimeters. Let's put 5 millimeters at the top. And cos, let's find this first. Should put this in my calculator. Cos pi divided by 2 times my square root of 40 divided by 59.218, and I'll just do that for now. Right, why am I going to get a negative answer? Oh, been naughty, naughty, naughty. The -1 needs to come here. Okay, so that's okay. Oh, I buckled this up completely. Right, so the sec becomes 1 over cos, then we have the -1, then we put all brackets around here, then the E comes here, and then the deflection is there. Sorry about that. So 5 millimeters, and we've got 1 over 0.27609, take away 1. So 1 divided by that answer is that, take away 1. So you got a kind of scaling factor here. So, 2 up to 10 maybe, the sort of numbers you're looking for. Times that by the 5 millimeters, and we've got maximum deflection of 13.11 millimeters. Kidoki. Right, so now that is max deflection, max stress. So I need to use the next formula. So that's D, now we're on part E. And again, it makes sense to be using this one because we've worked this out there, haven't we? So let's do that. So this is going to be straightforward. Let's plug in our numbers. Max. So this is the applied load. So let's put that all in SI units. So 40,000 divided by the cross-sectional area, which will be 30 times 10 to the minus 3 squared. So that's my area. And then we've got 1 plus, what's E? E is, now here we could work in millimeters. Got millimeters, millimeters divided by millimeters. So I think I'll do that. So we've got E is 5 millimeters. Yeah. Now the question is, what's C? Well, C is equivalent to your Y max. So it's the distance from the neutral axis to the side that you're expecting it to bend. So that will be your C distance here. Or the furthest away, really. So it's the equivalent to, so C is the equivalent to Y max that you would have done in the first year type problems. So the distance away from neutral axis is 15 millimeters. And what did we find? The R, it should really be RG. What's the RG? RG we found to be here, 8.6603. And we want to square that. Okay, now the sec is this term here, so multiplies by 1 over close the bracket, and that's it, job done. So let's work out this bit here first. So 5 times 15 divided by 8.6603 squared, and see if we get reasonable things as we go along. So we get pretty much 1 there. Divide that by 0.27609. Get the 3.6 before plus 1. So you've got a scaling factor on your stress of 4.62196. And here, if we just calculated the bit on the left here, that would be our regular stress. But your regular stress is getting scaled. 40,000. and your stress is now 205.4 megapascals. So a high stress value you're getting there. Okay, actually, was it stress or was it the force we was asked to find? Yeah, calculate maximum stress. So that's it. Okay. Leave it there, I think. Done everything. What we'd want to know is, I suppose, what the yield stress is or the maximum force.